Okay, let's just dive right into this explainer. Today we're tackling Physics Unit B 1.3. We are basically building a masterclass in thermodynamics here, starting from the totally invisible, tiny movements of particles, all the way up to the very real, very measurable rules that govern our physical world. Here's our roadmap for today. We'll be looking at matter, phases, and energy, then the potential energy trick, the three gas laws, graphing gas behaviors, and finally, solving thermodynamics questions. We're not just going to memorize formulas today. We're going to build a core framework of understanding. Starting with Section 1, Matter, Phases, and Energy, the microscopic rules of matter. We really have to ground our investigation in the kinetic theory of matter, keeping in mind that the microscopic behavior of particles entirely dictates the macroscopic reality.
Before we go any further, we absolutely have to distinguish between two crucial terms that get swapped all the time by mistake: temperature and internal energy. So temperature, that is strictly a measurement of the average kinetic energy of the particles. It's literally just how fast they're moving. But internal energy, well, that's the grand total. It combines that kinetic energy with the potential energy stored within the bonds that are actually holding those particles together.
Think about H2O. In a solid state, like ice, the particles vibrate, sure, but they're strongly held together. They're stuck in place by really robust bonds. But in a gas, like steam, those particles are completely free-floating, with absolutely zero bonds holding them back. It's crazy because the material itself hasn't changed at all, right? It's just the internal architecture of its energy that's shifted. This perfectly illustrates how the exact same material can have completely different physical properties just based on whether its particles are locked up tight or floating completely free. Now, to navigate the rest of this unit, you absolutely need a specific vocabulary toolkit for these phase changes. Going from solid to liquid, that's fusion. Liquid back to solid is freezing. Liquid to gas is vaporization. Gas back to liquid is condensation. Like the water droplets forming on a cold soda can on a hot summer day. And then we have the direct jumps. Solid directly to gas is sublimation, and gas straight to solid is deposition. You're definitely going to want to lock these into your memory for sure. All right, moving right along to Section 2, the potential energy trick, unlocking the physics cheat code. This concept can be a little counterintuitive at first, but learning it serves as a seriously powerful notation trick for your exams. So the secret to this physics cheat code is understanding that potential energy is recorded as negative when there are bonds present. Think of it kind of like being in debt. Because solids have very strong bonds, they possess deeply negative potential energy. You literally have to pay or, add a lot of energy to break those bonds. Liquids have slightly less strong bonds, so they have less negative potential energy. Basically, you're just trying to get that binding energy debt all the way up to zero. Which brings us to the magic number 0. If a gas has absolutely no bonds and therefore zero potential energy, why does it actually have the highest potential energy of any phase? Well, the crucial point here is that 0 is mathematically a higher number than a negative number. So even though there's technically no potential energy stored in a gas's non-existent bonds, it's actually at the absolute peak of the potential energy scale when you compare it to the debt of solids and liquids. Mind-blowing, right? Okay, let's jump right into Section 3, the three gas laws, the core framework. Let's reveal the suspects in our thermodynamic detective work. These are the rules that dictate exactly how these free-floating gases behave when we start tweaking their environments. Let's lock in the relationships across these three core gas laws. For Boyle-Mariotte, temperature stays locked in as our constant, while pressure and volume react to each other. For Charles' law, we keep pressure constant, watching volume and temperature do their little dance. And for Gay-Lussac's law, the volume is our constant, allowing us to track exactly how pressure and temperature scale together. Keep this matrix in your mind. It's literally the foundation for all the graphing and math we're about to do. Next up, Section 4, Graphing Gas Behaviors, Visualizing Pressure and Temperature. Now, what's really fascinating is how we can visually prove these exact relationships on a graph. When plotting pressure against temperature, like we see with the Gay-Lussac relationship, we get this really clear linear relationship. But the real trick here is the slope or the gradient. Based on the ideal gas law, this gradient equals nR divided by volume. So a steeper gradient mathematically proves a smaller volume. And while we're looking at pressure and temperature here, remember that graphing Boyle's law, which is pressure versus volume, gives us a descending curve. And Charles' law, volume versus temperature, gives us another perfectly straight linear slope. It is all about what you choose to keep constant. Finally, Section 5, Solving Thermodynamics Questions, the detective's breakdown. It's time to put all of these tools together to break down a rigorous, multi-step physics calculation, just like the ones you're going to face on your exams. Let's apply our core framework to a real scenario. If we're given an initial state of a gas and asked to find the change in internal energy, the temperature at specific points, and the total work done as it expands and compresses, well, where do we even begin? We just take it step by step. First, we establish the temperature at state B. Because pressure is constant here, we can just use the simple ratio of volume to temperature. By plugging in our initial states, we solve for the new temperature at B, which comes out to roughly 1300 Kelvin. With that locked in, we find the work done as the gas expands simply by multiplying our constant pressure by that change in volume. That gives us 4.8 kilojoules. Next, we bring in the first law of thermodynamics. Total heat energy added equals the change in internal energy plus the work done. And hey, we literally just found the work done. So to find the internal energy change for this ideal gas, we use our constant pressure formula, which yields 7.2 kilojoules. Add that to our 4.8 kilojoules of work, and we've just discovered that exactly 12 kilojoules of heat energy transferred into the gas. See, it all connects.
Finally, any full thermodynamic cycle has to account for energy going in and energy going out. By verifying that the net work done equals the total heat put into the system minus the heat released out of the system, we can basically balance our thermodynamic checkbook. Taking our 12 kilojoules in and subtracting the total heat out calculated from the rest of the cycle brings us to our very satisfying resolution of 2.6 kilojoules of net work done in one complete cycle.
So let's zoom back out for a second. Think about how these microscopic bonds govern literally everything around us, taking us all the way from the negative potential energy debt of a block of ice to the exact mathematical output of a mechanical engine. If the average kinetic energy, and therefore the temperature, doesn't change during a phase change, what hidden thermodynamic forces are actively shifting right before our eyes? The next time you watch a pot of water boil, remember, while the temperature plateaus at exactly 100 degrees Celsius, an invisible avalanche of energy is actively ripping molecular bonds apart right in front of you. Thanks for joining me on this explainer, and keep questioning the physical world around you.